Hello everybody, and welcome to our video on limits and continuity. So let's start with the definition. Let f be a function of two variables whose domain D includes points arbitrarily close to AB. Then we say that the limit of f of x as xy approaches AB is L, and we write the limit as the point xy approaches AB of f of xy equals L. If, for every number epsilon greater than 0, there is a corresponding number delta greater than 0, such that if xy is in the domain and its distance from the point AB is less than delta, then the distance of the output from L is less than epsilon. So remember, when we're talking about limits, a function might not be defined at the point. So this is our rigorous definition for our limit. And this basically says what we intuitively think of for limits, right? We think of a limit as being when the input gets really close, the output gets really close. But this says that precisely, right? This is our distance formula between the point xy and AB. And this magnitude here is the distance between our real numbers, f of xy and L. So all we're saying here is when the distance of the point xy is close enough, that number being delta, to AB, then we can guarantee that our distance between f and L is less than some number epsilon. The key here is that we can make this epsilon as small as we want, and as long as we can keep finding points within this delta that guarantee you get this output arbitrarily close to L, then we can say that this limit exists. So let's try to picture that a little bit in two different ways here. So the first is we're looking at a domain in the xy plane here. So this will be our x and our y. And so what we're saying here is that near this point AB, if you draw a circle out a distance of delta, so delta is the radius of the circle. What this says is that any point xy within this circle, when you map it on your function, it should output within this distance epsilon of L. So let's go ahead and take a look at this 3D model here, see if that helps a little bit more as well. Okay, so here we've got a 3D model. It's a sphere. And when we look at this sphere, what do we see? Well, this red circle here, this red disk, is the domain of the portion of the curve we're looking at. Or actually, I should say, it's not the domain. It corresponds to this circle in this graph. It's the portion of the domain that we're looking at. That's a distance of delta from AB. So what do we see? Well, when we look from above, from the z-axis viewpoint, which I can't get this thing to quite line up perfectly, but I think you get the picture. You have a circle there on the xy plane. And let's try to visualize this sideways a little bit, right? So what do we see here? Above the center of this disk is this point right here, this black point. And we see that this point, that's going to correspond to our limit for this function, the height of that point. So what we're saying is any point on this disk, any x and y value on this disk, maps to something that's within that little range, this upper y value and this lower y value. And the key here is that if we wanted to make this more accurate, if we wanted to shrink down this value of epsilon, we could do that, and we'd still be able to find a disk. Like the disk might have to get smaller, but we could still find a disk that would map within this tighter range of L. Hopefully that makes some sense. Now we'll see why we need this precise definition to deal with a problem later on, but for now, let's just move on to some other concepts. So, fact. If the limit exists, it must approach the same value from all possible paths. Therefore, if f of xy approaches L1, along a path C1 and f of xy approaches L2 along a path C2 where L1 and L2 are not equal, then we would say that the limit does not exist. So let's just look back at this picture again and kind of see how that relates to what we're looking at here. So what we're saying here is if we're on the sphere and we take any curve on the sphere that approaches this point, no matter what curve we take that's heading towards this AB value, we end up getting the same C value. We approach the same C value, no matter which direction we come from. So what we're saying here is if we approach from two different directions, so along two different paths, C1 and C2, and we don't get the same value, then the limit doesn't exist. This is analogous to what we think of in two dimensions. You know, we say, oh, well, the left-hand limit, say, approaches this, and the right-hand limit approaches this, and we would say, oh, well, at A, the limit doesn't exist. But in the case of three dimensions, it's much more complicated because there's infinitely many paths that can lead to that same point AB. So it becomes a little bit trickier. Let's take a look at this graph as an example of this. So this orange space here is a function whose limit at 0 does not exist. So why is that? Well, consider if you were traveling along the path where you're just looking at x equals 0, so along the x-axis, you see the z value is always 2 here. So along that path you would get 2. But on the other hand, if you were traveling along the y-axis, you would be approaching -2. So right there you see you're approaching the same 0, 0 point in the xy plane, but you get two different output values depending on which one you're approaching. All right, so let's do a couple examples of using this idea to show that a limit doesn't exist. So that's actually significantly easier than showing that a limit exists in 3 dimensions. So first we'll look at this, the limit as y approaches 0, 0 of x squared minus y squared divided by x squared plus y squared does not exist. So let's show that that's true. Okay, well, what we're going to do is pick some paths to travel along and check the limit with those paths. So we need to find a way to eliminate one of our variables so we can apply some algebraic techniques to calculate these limits. So first I'm going to just start out with a simple path. How about y equals x and see what we get there. So if we go to take this limit, well, if we're replacing y with x, this becomes just a limit as x goes to 0 of x squared minus x squared divided by x squared plus x squared. So our numerator is always going to be 0 here. But if the numerator is always 0, then this result is just 0. Okay, so let's try to come up with a different path here. How about let's try y equals the square root of x. Now, to be clear, it is entirely possible that you could choose 2 different paths and both would give you the same limit, but that doesn't mean that all paths give you the same limit. And actually this picture here is a perfect example. If we go back to this, you should see that there are a lot of ways you could travel along this curve and get 2 for your z value. There's a lot of paths you could take there. But it doesn't matter if there's infinitely many paths that take that. If there is a single path even that gives you a different value, then that limit doesn't exist. So I'm not sure if this one's going to work out, but let's just see. So if y equals the square root of x, then y squared is just x. So I'll factor an x on the top and bottom. Okay, so now we take the limit as x approaches 0 of x minus 1 over x plus 1, which is just negative 1 over 1, which is negative 1. And since 0 is not equal to negative 1, the limit does not exist. All right, so let's go ahead and move on to another example. So if f of xy equals xy over x squared plus y squared, does the limit as xy approaches 0, 0 of f of xy exist? Okay, well, that's a great question. Let's try that easy path again, y equals x. This is usually the first path I check, just because it makes everything a lot easier to work out. So then our limit will look like what? X is approaching 0 of x times x, which is x squared, over x squared plus x squared, which is 2x squared. X squared over x squared cancels, so this is really just the limit as x approaches 0 of 1/2, but the limit of a constant is just that constant, so that's 1/2. Okay, so I think about this a little bit. I get a value that's not 0, and so my guess would be actually to make y equals negative x, and here's why that's my next guess for a path. If I make y equal to negative x, my value in the numerator is going to become negative, but in the denominator, that negative x is going to get squared, so it's going to stay the same. So that should change the sign of the whole function's limit. So let's try that out. So y equals negative x. Up top, I get x times negative x, which is negative x squared, over x squared plus negative x all squared. So that's the difference here. This is x times negative x. So I can pull the negative in front, but here, the negative x is entirely inside this square. So when I square that, the bottom term becomes positive. It's x squared plus x squared, which is 2x squared. So now when I cancel here, I get left with negative 1 up top. So this limit is negative 1/2. And again, 1/2 is not equal to negative 1/2. So the limit does not exist. Okay, another example. So one of the things I want to point out here is just that the way you pick your paths is going to be unique for every problem. Every function you deal with is going to have different things you have to consider. So I'm trying to hopefully express, like in this last example, my thought process a little bit. But you might have to try multiple paths. It's totally normal to try 2, 3, 4 paths. Even if the limit doesn't exist, get the same thing for every one of those. And you just have to pick the proper path to show that it doesn't exist. But of course, the limit might exist, and we'll see an example of that momentarily. So let's take a look at this one. Does the limit of this function exist as xy approaches 0, 0? All right, so let's pick our first path, and we'll try y equals x, good old standby. So this limit will become the limit as x goes to 0 of x times x squared, which is x cubed, over x squared plus x to the 4th. So I factor x squared out on bottom, I get 1 plus x squared. X cubed still on top. X cubed over x squared is just x. over 1 plus x squared. And that's going to leave me with 0 divided by 1, which is 0. Okay, so now I want to think of another function we could try here, see what happens. So I don't want to get 0 again. So what I'm thinking is, if I could somehow make it to where I had x squared plus x squared in the denominator, that would give me 2x squared, and I could probably cancel that whole x squared with what's on top. But for y to the fourth to become x squared, y would have to be the square root of x. So we're going to take that path. So x times the square root of x squared is really x times x, which gives us x squared up top, and x squared plus x squared on the bottom. So this is x squared over 2x squared. The x squareds cancel, and we get left with the limit of 1/2. But the limit of a constant is just that constant, so that's 1/2. And 0 is not equal to 1/2, so we're done. The limit does not exist. Now, I've happened to choose correct paths to show what I wanted in each case here, but keep in mind it would have been very easy to come up with examples where I got 0 again for a limit. Like take, for example, if I'd chosen y equals x squared, I would have had x to the 5th power up here, divided by x squared plus x to the 8th power. And so I would have gotten a similar situation where when I factored the x squared out, I had 1 plus x to something, and I would have got left with 0 over 1 when I took my limit. So there's a whole bunch of paths we could have taken that would have led to 0 here. That doesn't mean that the limit exists. You have to, find two that don't work together, or we have to take an entirely different approach. So let's start talking about that. Okay, so fact, the basic limit laws from Calculus 1 extend to two variables. So things like the limit of a sum of two functions is the same as the sum of each function's limits. A constant times the limit is equal to the limit of the constant times the function. So that sort of basic stuff, but more importantly, the squeeze theorem still holds for 3 dimensions. Now, I'm not going to do a squeeze theorem example. Instead, what we're going to look at here is an example that's going to require us to use that formal definition. So, show that the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared exists. So, of course, if we checked a bunch of paths, we would get the same value. So we're going to check a path or two here real quick. So let's say, what limit might this be? Let's take y equals x, and this becomes the limit as x approaches 0 of 3x cubed over x squared plus x squared, which is 2x squared. That becomes the limit as x approaches 0 of 3x over 2. Plug in 0, gives us 0. Let's check one more path. How about something a little weirder, like y equals... How about x squared? So then we get the limit as x goes to 0 of 3x to the 4th over 2, not 2, let's try to erase that. Here we go. Of x squared plus x to the 4th. There we go. So that's the limit as x goes to 0 of 3x to the 4th over x squared times 1 plus x squared. That gives me x squared up on top, so this is the limit as x goes to 0 of 3x squared over 1 plus x squared. That's 0 divided by 1, which is 0. So those limits are both 0. Now, I might check a few more, and after checking a few more paths, I might start thinking, well, I'm pretty sure this limit exists. Usually, the first thing you want to do is check a couple paths anyways, because if you want to know what the limit is, you've got to at least check one path. But you might get lucky and find that doesn't exist. So, it's worth trying a few, and that's usually a little quicker and easier than the cases where we have to actually apply the definition here, which can be a little bit tricky. So we think that the limit might be 0. So we want to check. We want to check that the limit as xy goes to 0, 0 of the function is 0. So for any epsilon greater than 0, there exists a delta greater than 0 such that when the distance from xy to 0, 0, which is just x, the square root of x squared plus y squared, is less than delta, then the absolute value of the function minus L, which is just 0, is less than epsilon. Okay, so we just need to convert this last part here to our actual function, right? So our function is 3x squared y over x squared plus y squared. So we want that to be less than epsilon. But let me just rewrite this thing a little bit first, which is that x squared, 3, x squared, and y squared, all these are positive, so we can actually just write this as 3x squared times the absolute value of y over x squared plus y squared. So we want that to be less than epsilon. So in other words, what we're saying here is if we can show that for any distance away from 0, we can get our output arbitrarily close to that point to 0, as long as our inputs x and y are within a very small distance of 0, then the limit exists and is equal to 0. Okay, so I'm going to need a little more space here. Not too much more. So let's see what we can do with that then. Well, first of all, when I look at this function, what do I notice? I've got x squared divided by x squared plus y squared. So x squared divided by x squared plus y squared is clearly less than 1, right? Because x squared is going to be smaller than this sum. So that implies that 3x squared times the absolute value of y over x squared plus y squared is less than 3 times the absolute value of y. All right, now we got to get a little tricky. So obviously I'm doing this kind of quickly. When you're trying to figure out a problem like this for the first time, you might have to try multiple things. That's totally normal. And it might take a little while to find the correct approach. You got to be willing to play with these types of problems and think of them like puzzles. Of course, any puzzle where you already know the solution, it goes a little bit faster. So just keep that in mind. I already know how to work out this. I've practiced these kinds of problems many times. So sometimes it seems like, oh, you should just be able to pop it in your head like that. But really, it usually takes some time to come up with an approach to a problem like this. So, okay, moving on. I know that the absolute value of y is equal to the square root of y squared. And I know that this is less than 3 times the square root of x squared plus y squared. So why did I do that? Well, what I'm trying to do is figure out some way to relate my function to my delta and my epsilon likewise. So I want this whole thing to be less than epsilon. So if this expression was less than epsilon, then I'd be in good shape. So now I need to figure out the relationship. What does delta have to be to make this less than epsilon? Well, delta's got to be bigger than this square root. So if we made delta equal to epsilon over 3, so you're given an epsilon. What distance, what delta do we need for x and y to be close enough for our output to be close to 0, as close as we want it, epsilon close. So we're going to let delta be equal to epsilon over 3. Then what does that tell us? Well, that tells us that, what did we just see? We saw that the absolute value of our function minus L, which is 0, is less than 3 times the square root of x squared plus y squared, which is less than 3 times delta, which is equal to 3 times epsilon over 3, which is epsilon. So the limit is equal to 0. All right, that's it. We just showed that the definition for the limit was satisfied, and that problem is done. So one little extra note here before wrapping this section up. So the definition for continuity in 3 dimensions works just like the definition in 2D. A function of 2 variables is called continuous at a point AB if the limit as xy approaches AB of f of xy is equal to the actual value of the function f at AB. And we say that f is continuous on a domain D if f is continuous at every point in that domain. All right, that's it for this section. Thank you for watching.